Hi everybody! So in this next unit we're going to be starting to talk about finding areas and volumes using some of the calculus concepts that we've learned already this year. Let's start with reviewing what we already know. Up until now we have practiced finding the area between a curve and the x-axis. Now the way that we would find the area of a shape like this would be to integrate from a to b. So we would use the a and the b as our bounds. Whatever function we have in our problem. So in this case the function would be f of x. And we would put a dx here to finish the integral. And we've said that that helps us calculate the area that is shown in this picture. Next, what we're going to be working on is finding the area between two curves. So you'll notice that this area looks a little bit different. Instead of starting with f of x on the top and ending all the way down at the x-axis, we're finding the area between f of x at the top and g of x at the bottom. So here's what we're going to work on kind of setting up and figuring out how we would do that in this sort of video and notes. So let's talk about how we would do that. If f and g are continuous functions, where f is always bigger than g. In other words, f is always the top. We usually call this the top function, and g is always the bottom function. Then the area between those curves would be found using this integral. We would integrate from a to b, so we're still using the x values on the x-axis as bounds, and we would do f of x, which is our top function, minus, and we would use g of x, which is our bottom function. Dx. Now here's how this makes sense. If we integrated just our top function, which is going first here in our integral, we would be finding the area between f of x all the way down to the x-axis, all of this stuff. By subtracting the bottom function here, and we usually use the word bottom to describe which function that is. By subtracting the bottom function here, what we're doing is taking away this part of the area. So what we're going to be left with is the area that's in between. So we're going to be left with, visually here, the area that's in between the top and the bottom, which is the area that we were looking for. So, how would you set up the integrals for these functions? Well, you might be wondering, why are we just bringing up this whole top function and bottom function thing now? The reality is that in previous problems where the bottom was always the x-axis, the top function would be f of x, but the bottom function would just have been y equals 0. So if we still use this idea of top minus bottom, our integral would be from a to b of our top function, which is f of x, minus our bottom function, which is just 0. And since we know that subtracting 0 just gives us f of x, it would really just be the integral from a to b of just f of x. So what we've been doing up until now, although we've never said we're doing top minus bottom, really we have been, it's just that the bottom has always been 0 up until now. In the problems we're going to do now, your top function and bottom function are going to be two totally different equations. So when you set up your integral, you need to make sure that you have two parts to that integral, the top minus the bottom. Let's take a look at some example problems. For problem number 1 here, and we're going to do a variety of questions here, some with a calculator and some without. So problem number 1 here says, find the area of the region enclosed by this parabola and the line y equals negative x. Now to do that, I'm going to start always for every single one of these problems, particularly when you don't have a calculator, by drawing a really good graph. You want to make sure that you can see in the picture where the graphs intersect, what the region would be, where's the top, where's the bottom, all that good stuff. So I'm going to sketch a really good picture here. You'll notice that I'm using a straight edge to make nice straight lines for my graph. Now I'm going to go ahead and graph y equals 2 minus x squared in red. So I know that y equals 2 minus x squared is going to be a parabola. It's going to be a downward facing parabola, and it's going to be shifted up 2 spaces. So I'm going to use my ideas of parabolas to graph this. So I'm going to shift my parabola up 2 spaces. It's going to be upside down, so over 1, down 1, over 1, down 3. And my parabola is going to look like this. If you don't remember all of the details about graphing a parabola, that's totally okay. You can always graph this parabola by plugging in x values and computing your y values. So next I'm going to graph the line y equals negative x. I'm going to do that in orange. So y equals negative x is going to go through 0, 0, and the slope is down 1 over 1. So it looks like I get this line right here. The area that is enclosed, it says enclosed, by these two graphs would be this area right here in the middle. It looks like the intersection points here are going to be when x is negative 1 and when x is positive 2. So when I set up my integral, that will help me compute the area. I'm going to integrate from negative 1 to positive 2. Now what I'm going to do is try to figure out what is the top function here and what is the bottom. In this picture, the red parabola is above the orange line within this region that we're interested in. So the top function here would be y equals 2 minus x squared. So that's going to go first in my integral. Minus the bottom function here would be the line y equals negative x. dx. Finally, I'm going to actually compute the integral. So because this is a no calculator question, I'm going to start by simplifying the inside of the integral, which is going to be 2 minus x squared plus x dx. Then I'm going to do my antiderivative, so it would be 2x minus 1/3 x cubed plus 1/2 x squared plus c, and I'm going to evaluate that between negative 1 and 2. Next, I'm going to plug in the 2, so I would have 4 minus 8/3 plus 4 divided by 2, which is just 2, plus c, minus negative 2 plus 1/3 plus 1/2 plus c. The c's cancel, So I'm going to simplify the 4 plus the 2 and get 6. I'm going to save the 8/3 and making a common denominator for later. I'm going to go ahead and distribute this negative, so plus 2 minus 1/3 minus 1/2. And here's why I saved the 8/3 for later. I noticed that in the second, the parentheses, I would have a third. Again, I have the same denominator. 6 plus 2 is 8. Negative 8/3 minus 1/3 is negative 9/3, and negative 9/3 is just negative 3 minus 1/2. 8 minus 3 is 5, minus 1/2 is 4.5. So the area of that region that is shown on the graph would be this 4.5. For the next problem, what we're going to do is use our calculator, and it's going to make our lives a little bit easier. So if you don't have your calculator out, now's a good time to get it out. It says find the area of the region enclosed by the graphs of y equals 2 cosine x and y equals x squared minus 1. My first step here is going to be to graph those functions. So on my calculator, in the y1, I'm going to type in 2 cosine x, and in the y2, I'm going to type in x squared minus 1. I'm going to make sure I'm in my standard zoom, so I put zoom 6 to make sure I was in standard zoom, and I see this picture. Now I'm also going to make a note on my paper that I typed this function into y1 and this function into y2. That's going to be helpful for us in a little bit. Next, what I'm going to do is identify the region that is enclosed by these functions. It looks to be this little kind of, I don't know, looks like an I shape here in the middle. I'm going to sketch a quick picture of that on my paper. Now I don't need to be quite as precise with this picture as I was with the last one. I'm not using the picture to determine the intersection points and stuff like that. I've got a calculator, but it's still good to help us visualize what's happening here. So I'm going to sketch my cosine function. I'm going to sketch my parabola. And I'm going to identify the top and the bottom. It looks like the top function here for the region that I'm interested in is the cosine function. And it looks like the bottom function here for the region that I'm interested in is the parabola. I also need to know my intersection points. So I need to know this point right here and this point right here. To figure that out, I'm going to go ahead and use my calculator to figure that out. Calculate my intersection. The first ones I'm going to do is the positive one, which happens at x equals 1.265, and then I'm going to do the negative one, which happens at x equals negative 1.265. The region, again, that I'm interested in is here. Now, my sketch is not 100% accurate, but it gives me a good visual for being able to make sure that I'm setting up my integral correctly. In this problem, once I have my integral set up, I'm not going to actually have to do this by hand. I'm going to be able to type it into my calculator. So the area that I'm interested in here would be the integral from negative 1.265 to positive 1.265. And inside here, I would put my top function, which in this problem is y equals, sorry, not the y equals part. I don't know what I'm doing. It's just 2 cosine of x minus the bottom function, which in this problem is the x squared minus 1. Now here's, after I write that down, here's how I'm actually going to compute this. I'm going to go to my calculator. I'm going to go to Math 9. I'm going to integrate from negative 1.265 to positive 1.265. But remember how we typed this function into y1 and this one into y2? I'm just going to tell my calculator to recall those functions using my variables buttons. So I'm going to type in my y1 function first, because cosine, 2 cosine was the y1 function, minus, using my variables button, the y2 function, dx. And I should get 4.995. All right, that's the big idea for this unit. Now, we're going to do problem number 3 together in class when I see you again, and I look forward to practicing. See you then.